Lesson 40, types of reaction. We will look at some of the different types of reactions. That's going to be the goal for today. So jot this down. And we're going to go through what we did last lesson first, and then we're going to go through 4 different types of reaction. I'm going to try and do this relatively quickly. It's only 9:15 now, but the thing is that the last lesson that I gave you guys, the whole balancing chemical equations, that had a whole worksheet at the end of it. So I'm looking at that thinking that's going to take you guys a while to do. And I know that some of you guys still haven't finished lesson 1 yet. So I want to give you guys a chance to really get into it. So therefore, I want to give you guys a chance to work on some of the stuff. And so I want to use maybe the second period of today to give you guys, all right, done teaching, go work on some of the stuff. All right, so let's look at what we did last time. Last time when we had you guys, what we did was for the full day, we did balancing equations. First thing we did, and guys, you have to forgive me because we locked down so quickly at the end of last week. I'm not sure if the school has been closed completely. I haven't got my Wacom board, so I can't just draw on the screen like I normally do, which is really annoying. That's why I've got this jerry-rigged my phone to a clamp, and it looks really stupid, but it works. So what we did was we looked at the sodium metal explosion, which was one of the ones we didn't talk about, but it was one of the ones that pops up a lot. The idea with the sodium metal explosion is it makes a lot of hydrogen, and that makes big bubbles that explode out of the metal. But what I didn't say is there was actually 2 reactions. The first is the gas exploding out. The second is the gas can sometimes ignite because hydrogen plus oxygen can ignite to make water. What we then did was we then practiced counting atoms. I said, right, how many oxygen atoms? And I tried to teach you guys that if there are 4, is there a little number 4 here, that means there's 1 times 4. If there's a little number 3, then it's 3 times 3, which is 9. If there's a number at the front, which I should have an example here, but I don't because I'm not smart, you can then count that there is different amounts. So if there was a 3 here, there would be 3 times 2 is 6. Then what we did was we went over balancing. What do we need to do? You can't change the subscripts. You can't change it to NO4 because what that does is it changes the molecule. If you change H2O to H3O, then you've got a different molecule completely. But you can put a different number at the front. You should always start with the metals first or whatever the weird things first, and then move on to oxygen, hydrogen last, because usually water is involved, and water is not necessarily the easiest thing to balance. We balanced some simple ones, and then we went back after lunch, at the very end of the day, to balance some more complex ones. We balanced H2O2, which we struggled with because I was like, oh man, there are a couple ways to do this. And then but then I showed you this one here, which had a bit of a cheat at the end. And I remember showing you guys the cheat was, we're just going to make this 3.5, but then we'll multiply everything by 2. Now saying that though, you could still do this the slow way and get to the answer eventually. What do I mean by slow way? I think by slow way, I kind of mean like, let me see if I can show you. What do I mean by slow way? My understanding is this should work. This should work no matter what. So the slow way would be if I go H2O2 goes to H2O plus O2. If I count the H's on the left, I've got 1, 2. That's 2 hydrogens on the left. If I count the oxygens, I've got 2. Hydrogens on the right, I've got 2. Oxygens on the right, I've got 3. Okay, there's too many oxygens on this side. So that means I need to balance this by adding more oxygens to this side. So I can change this to 2. If I change that to 2, and that means that I've got now 4 oxygens on this side and 4 hydrogens on this side. Then you can be like, okay, well, how can I get around this problem? And you can keep balancing this out. Well, I need to add more oxygens to the right-hand side. Now, I could put a 2 out the front here, which would make more oxygens. Or I could put a 2 at the front here. If I put a 2 at the front here, I still get more oxygens. But instead of getting 2 more oxygens, I only get 1 more oxygen. So if I put a 2 here, then that oxygen goes 2 plus 2 makes 4. And then I've got 2 times the hydrogens, which is going to make 4 hydrogens. This is now balanced. Okay. Now the trick here is, and so you might have to make a choice like that sometimes. Oh, I've got oxygens here, or I've got oxygens here. Do I want to put a 2 here or 2 here? You should always look to see as like, well, you know, what's going to get you closer to the answer? What's going to get you to 4? You know, so just pay attention to, you might not necessarily be the simplest thing to balance. Then jumping back to the lesson, we did this one, which is a little bit harder, and then I gave you guys the rest of the time, which wasn't much time at the end, to talk about, to go start working the questions. Today what we're going to talk about is the types of reaction. Okay, now the first thing I want to talk to you guys with regards to the types of reaction is this: there are many different ways of grouping reactions. Okay, this is what makes it difficult. It's like saying, oh, there's many different ways that you can group music. You can group music as to like what genre it is. You could group music into how when it was made, as in was it made in the 1980s, or was it, you know, there are so many ways you can group of music. You can group it by album, by artist, yeah. So with chemical reactions, there's so many different ways that you can group them. You can group them by what the reaction makes. So you can group them by what starts the reaction. So it could be a light-based reaction. So you could call it a photoreaction. You could call it an electricity reaction because it starts with electricity. You could talk about it with what chemicals are involved. Oh, it's an oxygen combustion reaction. Well, that means oxygen is involved. You know, if it's a reduction reaction, that means that electricity is involved. But what we're going to talk about today is specifically, we will explore how reactants move around after reaction. So that's the types of reaction we're going to talk about. The interesting part for us is we're actually not going to look at, we actually don't care about what chemicals are involved. They could be nitrogen, oxygen, they could be whatever chemical that we want. What we're interested in is how does the what we're more interested in is how do chemicals change in this reaction. So how do we go from, how do they move around, like what changes in them? So that's what we're going to be focusing on. It's this one on the bottom. Okay, I'm going to give you guys a fraction of a second longer to jot this down. There's a pencil here. But yeah, after we finish today's lesson, what we will do is we will go back, we'll talk about different reactions. So we'll talk about, for example, oxidation reactions, and I'll talk about precipitation reactions. And what I want you guys to do is like go, oh, the precipitation reaction, yeah, sure, but that's just another name for this. So I want you guys to understand that. I'll give you guys a minute to copy this down, and then we're going to change the slide.
You can move on now.
Well,
Yeah.
I was about to change it anyway. Here we go. All right. So we're going to talk about 4 types of reaction. Okay. Now, these types of reaction, as I said, the first one is called a combination reaction. Now, in a combination reaction, or sometimes known as a synthesis reaction, these are when 2 or more reactants combine. I'm missing a word here. I'm missing the word combine. So I'm not going to put that in because it'll crash the whole thing. But as soon as just A, if I take a reactant A, whatever A is, A could be anything, plus B, whatever reactant B is, B could be anything. They come together to make a new molecule, one molecule. There are less products than there are reactants. There are more reactants than products. We lose reactants. We don't lose them, we just don't have as many. It's called synthesis because you're making something new, you're synthesizing and producing something new. Now, and again, notice here that there's no chemical names. I'm not saying it has to involve oxygen. I'm not saying it has to involve carbon. It's just any time the 2 things come together to make a new thing, one new thing. It's like taking 2 Lego blocks and joining them together to make a new Lego block. That is a synthesis. Underneath that, I've got an example. An example of this type of reaction is the formation of titanium dioxide. I could have taken any oxygen reaction. I chose titanium dioxide, so titanium plus oxide makes titanium oxide. We've got 2 reactants on the left and 1 product on the right. 2, 1. Notice as well that they combine to make titanium dioxide. Now, some cool facts about titanium dioxide. Titanium dioxide is a white powder. It's not just a white powder, it's one of the brightest whites you can get. It's actually used a lot in different dyes. That's why on the right here we've got a picture of some A4 paper, is because all white paper has titanium dioxide in it. If you are writing on a piece of white paper right now, then you are writing on a piece of paper that's being dyed with titanium dioxide. Because normally paper is yellow. Titanium dioxide is also a really main ingredient in a lot of foods. It's also toothpaste. If you've ever had toothpaste, guess what? It's got titanium dioxide in it to make it look white. So yeah, it's a white product. You don't need to know that, but you know, whatever. This is also above an oxidation reaction. As oxygen gets added, what that means is that oxygen is going into the titanium. Now, and that making a new product, which is the metal plus the oxygen. This type of oxidation reactions are usually combination reactions. So if I replace this, let's say instead of titanium, I use iron. Iron plus oxygen makes iron oxide, which is rust. That is a combination reaction. Copper plus oxide makes copper oxide. That is a combination reaction. Even carbon plus oxygen, if you burn it, make carbon dioxide, is an oxidation, is a combination reaction. So the very first one that we're talking about today, combination reactions, 2 things coming together to make a new thing. That's it. And when I say coming together, I literally mean sticking together. All right, I'm going to change the slide in about, what, say 30 seconds? Unless you guys are already cool and I can change the slide now.
Yeah, I'm good.
I'm good too.
You're good too?
No, I just need to copy down the last line.
Oh.
Okay, so I'm going to change the slide now. Here we go. The next one is decomposition reactions. Decomposition. So decomposition, of course, if I've got a combination reaction, two things coming together to make one thing, I should talk to you guys about the opposite. The opposite is a decomposition. This is the opposite, involves a reaction breaking apart into smaller products. So let's compare the numbers here. I'm going to flick back a slide here. One sec, hold on. We've got 1 plus 1. We've got 2 on the left, 1 on the right. Notice this one we've got 1 on the left and 2 on the right. There are more products than there are reactants. This is how you do a decomposition. And guess what? We've already seen one of these. You take H2O2, you turn it into H2O plus O2. We've got one reactant on the left, and we've got 2 reactants on the right. 2 products on the right. Some of you guys will be saying, yeah, but sir, look, there's a 2 here. Like, yeah, I get that, that's fine. But the main, I guess the thing that you want to look at is not necessarily how many, what I think is more important is not necessarily how many of each thing there are, but the fact that, one, there are more products than reactants. That's the first important thing that I think is worth seeing. And the second thing that I think is important to see is that there is only one molecule. There's only H2O2 on the left, whereas there's 2 different types of products on the right. Many explosive reactions are also decomposition reactions, because essentially what they do is they decompose into hydrogen or nitrogen or whatever, and then you end up with a lot more of that. So decomposition is the opposite, is breaking apart a complex molecule into a smaller molecule. I'm going to give you guys, 30 seconds from now. If you need more time after 30 seconds, we can go back to it at the end. Yeah. Okay. Yeah, it's been about 30 seconds. So, oh, by the way, on the right, I guess I should talk about this picture. This picture is an example of something called, it's a very highly photographic one still. This is something called elephant's toothpaste. What it is, it's actually this reaction with hydrogen peroxide. That's what this is, if you didn't know. And what you do is you react the hydrogen peroxide with a little bit of, I think from memory, usually yeast or something. And what it does is the yeast doesn't actually react. All it does is it starts this to make water and oxygen. And all that oxygen just pours out as a gas. And what you do is you just add a little bit of detergent. Because you have dishwashing detergent, it makes millions upon millions of bubbles, and they actually spurt out and then overflow. It's kind of cool. I've seen it done before. I've never really done it myself because it makes a bit of a mess. And also because it's actually a chemical reaction, sometimes people forget that these bubbles actually start steaming. They're really, really hot. But you know, it's just something. All right, so that's number 2. So far I've done combination, coming together, decomposition, falling apart. So what's next? Next is something called a single displacement reaction. Okay. This reaction involves one new reactant moving into a compound and taking the place of another reactant. What does that look like? So here I've got, in this example, I've got A and B, and A and B are bonded together. And then I've got this new element, this new reactant coming along, C. What C does is C goes, get out of the road, B, you know, hit the road, I'm out of here, I'm taking your spot. So so C takes the spot of B. So then it's now AC, with B left, you know, all lonely on the outside. You know, it's like, you know, two people are dating, this new person comes in, swoops in, steals the girl, and then there's a loner boy left over afterwards. Anyway, what happens?
Is that how I should think about it?
Sure. If
So I
that's how
just
you
think,
want.
you know, a guy just comes in, takes that girl, and the guy's just there,
Bruh.
alone, you know, and abandoned. All right
Listen,
then,
yeah, if that's how you remember it,
easiest way.
I'm going to warn you, Brendan. If that's how you remember this one, just wait. Just wait until we get to the next example.
God damn. The guy probably has a child with the wife and abandons the child and takes the wife.
Bro, that's so sad.
Anyway, moving away from the sad, depressing things, let's go have a look at this example here. So in this one underneath, the formation of magnesium chloride. So here we've got hydrogen and chlorine. And these two are bonded together. You got this magnesium, that's the C here. So the magnesium comes in, swoops in, and takes the place of the hydrogen, right? The hydrogen, well, he gets kicked out. He's a loner boy, so he gets over here and he gets turned into a gas. And yeah, obviously we've got to do a little bit more for a particular reaction like this because we've got to make sure it's balanced. But you can see here, I actually don't care about, as I said, the same as the decomposition. I don't care about the coefficients. I just care about what's happening. The magnesium is taking the place of one of these chemical of the A and therefore forcing the other one out. Okay, that's what I really care about here. Now, you might think, oh, this is a decomposition reaction, but it's not. It's changing. It's one thing is swapping in, the other thing is swapping out. You can also tell it's not a decomposition because what you can do is you can count. There is two types of molecule on the left, and there is two types of reactant on the left, and two types of product on the right. Notice I'm saying types. I'm not saying the amount of reactants. I'm saying the types. So that means that's how it's worked. This is an example of a metal acid reaction. You can actually see in this reaction, this is how it works. We've got a magnesium ribbon in here, and that's going to react with this HCl, which happens to be an acid. Hydrogen's going to get produced, so that's why you see these bubbles. And that white film on the outside of the metal, that's the MgCl2. So, yeah. We're going to go through one more, I think. But I'm going to give you guys, another 30 seconds to get this one down. Then we've got the last one coming up. As I said, there was only 4, so... All right. So next up is the very last of our 4 reactions. Hey, don't make me kick you out. All right. Very last of our 4 reactions, which is the double displacement reaction. Now, if this one, and this is the reason why, Brendan, I was saying get ready for it. If this one is a cool dude, like a cool guy swooping in and stealing another guy's girl, This one is a swingers party. Literally in this one, people just swap partners. You know, hey,
Yikes.
your wife's hot. Do you want to swap for the evening? Yeah, sure. You can have my wife. Yeah, hey, that sounds fun. A and B react with C and D. So A goes, hey, you know what? Your wife D, she's pretty hot. And so they swap. So A gets with D, B gets with C, gets with B. And then you swap partners. This is called a double displacement. For those of you that, I know some of you guys are not going to be thinking of love, like, you know, some kind of swingers party and swapping partners. The reason why it's called a double displacement is not just B is swapping partners to C, but D is also swapping with A. You get a double swap. I forgot to get a
So they're
picture.
basically taking turns, right?
Yeah, they're
Oh,
swapping
yeah.
partners.
Ew.
Ah, okay.
So why
Cool.
would we think about?
Let me see. There was a picture I was going to show you guys. Let me see if I can find it. Hold on. Hold on. I think I'm going to have to maybe. Ooh, double displacement. There was like.
The thing is gone, by the way.
I know. It's all right.
What?
Oh.
It's like, yeah.
So, how long do you think you guys are gonna stay home for? Like the teachers?
Hold on.
Oh,
I'm going to do this. I know you guys can't see this, but that's all right. I'll just plonk this down the bottom here like that. I like that. Okay. And then I'll go back to the Zoom. We're gonna go share over here. Bang, bish, bash, bosh. And whoop, share from this slide. Done. Okay. So in this one here, the picture down the bottom is the new thing that I've added here. So if you look at this picture down the bottom, you can actually see that D goes over to where A is. So, and B goes over to where, and then, yeah, so D goes over here, the other one swaps. And so you end up with this swapping process going on. This is a bad picture, unfortunately. I think they also got the arrows in the wrong direction. I think one of these should be the other way, but whatever. I don't really care too much. Here is the
Wait, so,
example. Yep. Yep.
So, let me get this straight, yeah? So the A's, yeah, basically go AA, right? And then like the B's like BB, yeah? And it just keeps going, right?
Yeah, so they just swap.
Oh.
They just swap their places.
Uh-huh. Alright, cool.
So this one here is the formation of something called lead iodide. Okay, so how does lead iodide get made? So what you do with lead iodide is you take lead and nitrate. And lead nitrate, if you react lead nitrate with potassium iodide, then the lead nitrate, hold on, let me just kick these dogs out. Come on, get out, shoo, being too loud.
And somebody call RSPCA, bro.
Why is he kicking the dogs out? They're not doing
Because
anything.
it's barking.
barking.
The
No,
business
they're
barking.
just chilling, man. What do you mean?
I know, right? Let's call
So your
RSPCA.
dogs are just chilling. Why are you kicking them out?
It's just barking. It's just like the kids
What's that? Their barking means they love you.
They're barking.
Oh, okay.
They're barking because they're
Okay.
looking out the window and they're like, "Oh, who's this walking past the window? I better
They're trying to
bark."
find a girl, you know? They're trying to find a girl with a guy already. They're trying to take some action, you know?
Are you telling me you can understand what your dogs want?
Well, my wife just left the house and then she just came back, and then I think they got really excited. It's like, "Oh, I can see her out the window." It's like, "Yeah, she's still coming in." Whatever. I think.
Crazy.
No, so they just love you.
I think my wife just got me coffee. So
Yeah.
like the big one's awesome because he just comes in, sits down, and doesn't bark. The little one, she's bark all the time. So
What's a little one? Is it like a chihuahua?
no, it's a fox terrier.
A
So-
what?
Oh, What the fuck is that?
Yeah, I was like,
If she comes back in, I'll show you. You know.
Oh, these dogs! Yuck! I hate the legs, right? I think the face is alright, but like the legs are disgusting. Ugh.
Anyway, let's just finish the double displacement reaction. So first things first, how does it work? So you've got here lead nitrate. So lead, it's got nitrate here is its partner. So the nitrate swaps from the lead and goes to the potassium. So you can see NO3 is attached to the nitrate. In the end, the NO3 is attached to the potassium. It swapped its partner. The other example here is the iodine. The iodine is attached to the potassium. Yeah, that swaps its partner with the. Hello. Thank you. These two were barking, and they were. Well, this one was fine. The little one was barking.
I know, she's looking at the dog.
Yeah, I know. So the little one, what am I talking about? So the iodine, it jumps from the potassium over to the lead. That's why you can see it's initially attached to the I. So if the iodine is the D is attached to the C, and then at the end it's attached to the lead. They've swapped partners. This is so double displacement is like a swingers party. By the way, the reason I love this one is because potassium iodine makes a beautiful yellow compound, and it's actually what was used a long time ago to make yellow paint. I say a long time ago because it's not used anymore because lead is toxic, so we don't. Yeah, but that's not the point. The point is that they swap partners. Okay, I'm going to change the slide in a sec. Are we cool if we change the slide now?
Yes, sir.
All right, let's jump on. So after this, the next part is I've just got these 5 examples here. You don't have to write these down. I want you guys, I'm going to give you guys a minute to do this. I want you guys to look at each of those and guess, do you think they are, number 1, a combination? Do you think they're a decomposition? Do you think it's a single displacement or a double
are
displacement?
they all the same?
They are not all the same. So all these are different. I think some of these are, one of these is definitely a combination. And I think there might be two of one of them. So have a look, see what you think, and then we'll go through them together.
Okay.
Wait, can you go back to the first one and explain that for me?
Which first one?
The first one, combination reactions.
So I'll leave this slide up just because I want people to be able to do it. But a combination reaction, right, just means that 2 things are coming together to make a new thing. So if you want to tell one of these here is a combination reaction, the fastest way to tell which one is the combination reaction.
Oh, it's the 5th one.
Yeah.
Right?
Yeah. Because coming, it's 2 things coming together to make one new thing. So that is the combination.
That's combination. Yeah. Wait, so then. Oh wait. Hold up. Oh wait. What the freak?
Yo, Mr. Grill,
Yep.
I'd like to say that the first one is a decomposition reaction. Am I right?
You are right. The first one is
okay.
decomposition. Why do you think the first one? How did you come up with the first one as a decomposition?
Because you see, you know the product here.
Yep.
It's like one thing. Like it's not breaking up, but like if you look at the reactants, you know, like like the first reactant, it's breaking up, and while the second one it's also breaking up, and if you add them all together and you balance all the things out, they're equal to the first product.
Yeah. The main reason that it's a decomposition is because you start with one product at the start, and then that breaks up into two smaller products.
Uh-huh.
And that's exactly what a decomposition is. You're starting with two. What about this? Can someone tell me this second one? What's this second one?
Is that a double
Yeah, I
displacement
want to say.
reaction?
That is a
Yeah, that's a double.
displacement. Because
Especially
what-
Felix.
if we watch this, the NO3 jumps from the silver over to the sodium, and then the chlorine jumps from the sodium over to the silver. This reaction here is makes silver chloride, which is actually really cool because it's a solid, so it's a good way for food chemistry. If you ever do chemistry, what they do is they do this reaction because they use it to find out how much salt is in something, because all the salt turns into a solid, so you can find out how much salt. What about this third one?
I'd like to say that's what's that shit called? Single displacement reaction.
Yep. So you've got potassium. You are correct. You got potassium sitting in. You got iodine sitting here with his girl potassium. Bromine comes over. Well, he's bromine. He's a bro. He comes over, flexes his muscles. Potassium goes, I'm going to saddle up with the bromine. The iodine gets left out in the cold. So yeah.
And the last one is, I don't know what that's. I forgot what the last one is. Well, you already know what the last one is.
What do you guys think about this last one? It's actually probably the hardest one here.
The hardest?
Well, I don't know, maybe.
Wait.
Wait a minute. Look.
I reckon that's a single displacement reaction.
Yeah, it looks like a single to me.
Why do you guys think it's a single displacement?
I don't know.
Well, let's run through our rules, okay? Is it two things coming together to make one thing?
No.
No, so it's not one.
It's not.
Is it one thing breaking up into two things?
Yeah.
Yeah.
So the oxygen jumps ship and
No.
joins the 2Na.
But yeah, so it's not two either. It's not a decomposition. So it's either going to be 3 or 4. We've got
It's a combination.
It's not a combination because you've got 2 things on the left and 2 things on the right. You're not making. This
what a
one
bummer.
here is actually, you guys were correct at the start. I was just trying to get you guys to figure it out. This is a single displacement reaction.
What can I say, sir? What can I say? I knew the whole time, sir. I knew the whole time.
The reason why this is a single displacement reaction is the sodium, the hydrogen's got H2O, right? Got one, and what happens is the sodium comes in and takes the place of one of these hydrogens. That's why you end up with NaOH. The other hydrogen gets kicked out, and that's how you get H2O gets kicked out. The best way to see whether something is a double displacement reaction is to look, single displacement reaction is to look to see you have one thing going in and you have one thing coming out. So that's the easiest way that you can check to see it. Whereas if you look at the double displacement, you've got, 2 different things going in and 2 different things going out. So I guess the thing is that you've got just a sodium going in and just a sodium coming out. It's just a bromine going in and just an iodine coming out. So that's the best way to pick up. On the right here, by the way, this is these are vases made out of cinnabar. The cinnabar was a popular dyeing material. As a compound that they used in dye. It was actually this bright red, and it's actually this material over here, HGS. So cinnabar is, sorry, where is it? Here. Cinnabar is actually mercury sulfide. So that's what cinnabar is, and that's why it's bright red. It was used a lot in.
Isn't that poisonous?
It would be poisonous, yeah, because it's got mercury in it.
Yeah.
So you probably don't want to be drinking out of this thing, which is kind of bad because it is a vase or it is a pot. But of course, they didn't know that it was poisonous back then, so it's hard to blame them. The very last thing I was going to talk to you guys about at the very end is you guys are now going to work on, spend the next period working on style, which is, well, when I say next period, I mean the next about 40 minutes. And a lot of style deals with, they talk a lot about this, which is called the Haber process. Now, the Haber process was a process that was made by Fritz Haber or Haber in about the 1910s. And what Fritz Haber did, and like I love this story because it's got a fair bit of, it's got, in my opinion, science doesn't have enough of this. It's got a bit of moral dilemma. You guys hear about moral dilemmas all the time when you do, when you guys do, what's it called, humanities, because I talk a lot about like, oh, this person was bad, this person was good, this person did this for their country. We don't talk about it in science. Fritz Haber was I believe he was a German chemist. And in 1910, there was a massive issue, especially in where there was an issue in, I think, Ireland, where there was a famine, and there were famines around the world. And essentially they couldn't make very much, agricultural products. They couldn't make a lot of wheat or a lot of potatoes or anything. What they would do is they'd make fertilizer. Problem is fertilizer needs a lot of ammonia, NH3. You can make different fertilizers for ammonia, but you need ammonia. The only way to get ammonia is to get it from animals or to mine it out of the ground, and that was actually very, very expensive. But what Fritz Haber did is Fritz Haber found a way that you could change nitrogen and hydrogen and combine them to make ammonia, and he actually made a process that actually made that work. By the way, firstly, is this what type of reaction is this? Is this a combination, or is this a
that's the combination reaction.
It is a combination. We're taking two things. We're taking nitrogen and hydrogen. We're making something new. We're making ammonia. This is a synthesis. That's why it was actually called the ammonia synthesis reaction. So this actually, he went to make ammonia, and it was actually really, really good, because what that meant is now a lot of countries could then make their own fertilizer, so they could then plant their own, they could then make lots and lots of vegetables, and so they could feed their countries. And it's a really, really good thing. So Fritz Haber essentially saved a lot of people's lives. But there's a twist to this story, and I always like this twist. I really should have had a picture of him over here, but I made this slide really, really late at night. The twist with Fritz Haber is that he also took this new chemical ammonia, and because he had now access to large amounts of ammonia, he used it to make something called, that would essentially change the way that that war was conducted. What he did is, because he had access to ammonia, he created something called mustard gas. Have you guys ever heard of mustard gas before?
Oh, isn't that what Adolf Hitler got gassed with? That shit. Makes your eyes like red.
What it does is it poisons people.
Yeah, basically.
And what they would do in the war is, and this is the First World War, is that they would, because leading up to the First World War, you know, you would have a bunch of people with guns and swords, and they would charge each other, and they'd shoot each other, and then that'd be, you know, that'd be it. That'd be done. You know, kill each other. You'd have a couple of cannons, and you know, that'd be it. But now what he did is he invented a new type of warfare, chemical warfare. What they would do is they would drop bombs of mustard gas, or throw mustard gas grenades, and they would get into a trench and just poison everyone in the trench. The problem with chemical warfare is that, and this is what I find interesting, is that chemical warfare is same sort of thing as a little bit like biological warfare, which I don't think has really been done too much, but and same sort of thing as nuclear bombs, is that with chemicals, they can't tell who the bad guys are, who the good guys are. They can't tell the difference between an innocent child and or an injured person versus a soldier that's going to come kill them. It just kills everyone. So that's kind of why I don't like chemical warfare. At least if you've got, as bad as warfare is, at least if you've got a gun and you shoot someone, you like, there is a human being in control that can at least make a decision, whereas chemicals can't. So that was one of the things that Fritz Haber did, and Fritz Haber actually helped out a lot with the warfare, trying to do that. In the Second World War, it was used a little bit less, because in the Second World War there was, I think, less. It wasn't really much about. There wasn't as much trench warfare, so it wasn't like people digging. When I say trench warfare, I mean people digging trenches and hiding out in holes and jumping out, and quickly trying to kill the enemy and jumping back in their holes. That's what trench warfare is. There wasn't as much of that in Second World War. So Fritz Haber, yeah, is he a good guy? Yes, he invented, a synthesis that allowed him to make fertilizer to feed many, many nations. Even now, we still rely on that same process to make fertilizer so that third world countries can eat food. Is he a bad guy? Well, kind of. He helped invent chemical warfare and encouraged different nations to use this deadly chemical to kill people. I don't know, it's interesting. But so this is actually the main focus of the style. So that's actually what you guys are going to work on now.